Welcome to the deep dive. Today, we are taking a close look at this really intense technological race that is going to define global mobility.
It's a battle for the battery.
Exactly.
Yeah.
The shift to electric is happening. We all see it. But the real question now is, not if we go electric, but how. And more importantly, which battery technology is going to power this massive $400 billion industry of the next decade.
And we really need to pause and just grasp the scale of this. It's an almost unprecedented industrial expansion.
Right.
Global demand for the current lithium-ion batteries. It's set to just soar from around 700 gigawatt hours in 2022 to get this, about 400 and 700 gigawatt hours by 2030.
Wow, that's a six-fold increase.
A six-fold increase in less than 8 years, and this is creating a colossal new industry and mobility, EVs, that's the bulk of the demand.
Which is why this deep dive is so essential. We have sources that compare today's workhorse, the liquid lithium-ion battery, or LIB, with the big challenger everyone's waiting for, the solid-state battery, or SSB.
The incumbent versus the disruptor.
Yep. And our mission today is to give you a simple, clear understanding of the technical hurdles, some really surprising math on the performance gains, and the huge commercial and environmental challenges this whole sector is facing by 2030. Okay, let's unpack this. Where do we start?
We have to start with the technology doing all the heavy lifting right now, standard LIBs.
Okay.
I mean, they've been the undisputed champion since the early 90s. They use oxide cathodes, carbon anodes, and a liquid electrolyte. They're reliable, they're pretty energy dense, and we know how to make them at a massive scale.
But they have these fundamental flaws that the industry is just desperate to fix. The biggest one is safety.
That's the one. The liquid electrolyte's flammable, it's hazardous, and that means car makers have to build these heavy, complicated, and expensive safety casings around the battery pack.
I see.
And for you listening, if you're thinking about buying or investing in an EV, those flaws really show up as two main pain points. First is cost.
How much of the cost is it?
The battery itself is estimated to be about 37% of the total cost of a car, like the Tesla Model 3.
A third of the car's price.
Wow, exactly. And the second is performance. Range anxiety is still a real thing. For EVs to truly take over, we need cars that go further and charge way faster.
But what's really surprising, I found, is how successful the current liquid lib tech has been at pushing down those costs, even with those flaws.
It is a phenomenal commercial success story. If you look at the cost curve for libs, the cost per kilowatt hour has just plummeted since 2010.
And that's the gigafactory effect, right? Just economies of scale.
That's it. Massive scale and constant manufacturing improvements. Our sources project that the current chemistry, the liquid ones, can and will hit cost parity with gasoline cars.
So that's the famous $100 per kilowatt hour line.
That's the magic number, and we'll likely hit it within the next 5 years.
Okay, but hold on. If we jump ahead a bit, the sources also talk about this huge raw material crunch, like a predicted 55% lithium shortage by 2030. How does that cost parity hold up? Doesn't a huge shortage just wreck that whole cost curve?
And that is the central tension in this whole industry. The 100 kilowatt line is doable short-term, based on manufacturing getting better. But you are absolutely right, the long-term view, post-2030, that is massively constrained by supply, which makes the whole circular economy idea we'll talk about later absolutely critical.
Got it.
But for now, the most obvious way to improve the tech itself, putting aside materials for a second, is to fix that performance issue by replacing the carbon anode with pure lithium metal, or LIM.
That's the technical prize. Why is lithium metal so much better?
It's all about capacity. Lithium metal offers roughly 10 times the gravimetric capacity, so the energy storage per gram of the carbon anode we use today.
10 times. So if it's that much better, why aren't we using it now? This gets us to the boogeyman of battery tech.
Dendrites.
It's the dendrite catastrophe,
Yeah.
exactly. When you have a pure lithium anode and you cycle it, charge it, discharge it, the lithium doesn't move back and forth uniformly.
Instead, it forms these tiny, sharp, needle-like structures. They're called dendrites. You can picture them growing inside the battery like microscopic icicles.
And as those little needles grow, they start to push through the separator material inside the battery,
Yep, they migrate across until they finally touch the cathode on the other side.
creating a short circuit.
A dead short. And because those early cells from companies like Moly Energy and Exxon back in the 90s used that highly flammable liquid, that short circuit caused the cell to just ignite or explode.
And that's why the industry had to abandon it and pivot to the much safer but less powerful carbon anode.
Right, and that failure is the exact reason solid-state batteries were conceived. The whole promise of replacing that flammable liquid with a solid-state electrolyte in SSE is really twofold.
Okay, what are the two things?
Well, first, the obvious safety one. The solid electrolyte is generally way less flammable. And second, and this is the key performance part, the theory is that this rigid solid material acts as a physical barrier.
It's supposed to be tough enough to just block the dendrites from punching through.
Exactly. And if you can block the dendrites, you can safely use that high-capacity lithium metal anode. And that represents a potential, about a 20% upside in the whole battery's energy density compared to liquid lids today.
Safer and with significantly more range. That's the dream.
That's the dream.
But here's where it gets really interesting. The theory is great, but the reality is much, much harder. If that 20% gain and huge safety improvement is on the table, why aren't all the gigafactories switching over right now?
Because the reality is that currently, no reported solid-state battery meets all the key performance metrics of a top-tier liquid battery. We're talking charging rate, long-term life, all of it.
And this is where we have to look past the hype and actually look at the math.
Yes. The expected gain from using an anode that's 10 times better isn't a cell that's 10 times better. The cell's total capacity is limited by its weakest link, which is still the cathode. The relationship isn't linear. Think of it like two resistors in parallel.
So the cathode is the bottleneck. You can make the anode 10 times better, but you only get a modest gain overall because the cathode can only hold so much energy. Is that it?
You've got it. When you factor in everything else in the cell, the packaging, the current collectors, the weight of the cathode, the math shows that future SSBs using lithium metal and a low-density solid electrolyte are estimated to hit about 480 watt-hours per kilogram.
Okay, 480, that sounds pretty good.
It does, until you realize that future liquid labs, the ones without lithium metal, are already projected to hit 400 wattage kilogram.
So the gap isn't this revolutionary leap. It's a really tight race.
It's a very tight race, and it gets even tighter depending on what the solid electrolyte is made of.
How so?
Well, if an SSB uses a dense, stable material, like a specific oxide, a garnet they mentioned in the research, the theoretical energy density drops to only 375 wattage kilogram.
Wait, so that's actually worse than the future liquid batteries.
It offers no energy density upside. So the only way SSBs can even compete on performance is if they can create a solid electrolyte that's both super protective and incredibly light. Low density is an absolute must.
That puts a huge constraint on the materials. Okay, what about longevity? This hinges on a tiny, often overlooked number, Coulombic efficiency, or CE. Why is that one number so critical?
CE is just the ratio of charge that comes out of the battery versus what you put in. For a battery to last a long time, that ratio has to be almost perfect.
And why does that 0.01% matter so much?
Because that tiny loss means a little bit of the active lithium is getting permanently consumed in side reactions every single time you charge the battery. It's like a tiny bit of fuel being burned off and lost forever.
So over thousands of charges for years and years, that tiny loss adds up.
Precisely. Current liquid leads need an average CE of greater than 99.99% just to keep 74% of their capacity after 10 years.
Okay, greater than 99.99.
Now, if that CE drops just slightly to 99.98%, that microscopic 0.01% difference, the capacity retention after 10 years plummets to just 55%.
Wow. So for the person buying the car, that tiny margin is the difference between a reliable battery and one that fails way too early.
It's everything. Any new SSB has to meet or beat that incredibly high standard.
So with all these tight constraints, density, performance, that crazy efficiency number, the research money is focused on three main families of solid electrolytes. What are they?
The three main groups are sulfides, polymers, and oxides. Sulfides are, sort of the front runner on paper right now.
Why is that?
They have really high conductivity, so they can charge fast, sometimes even faster than liquid electrolytes, and they're low density, which is great for the overall range.
But there's a huge catch with making them, isn't there?
A massive one. Their main problem is air stability. They react instantly with moisture in the air and form toxic hydrogen sulfide gas.
That sounds like a manufacturing nightmare.
It's an enormous challenge, and on top of that, they're not very stable where they touch the anode and cathode, so they often need complex protective coatings.
And when you look at the actual cells people are building with these, the real-world performance shows the trade-offs. I saw they're still built with really thick electrolytes. One example was 240 microns thick.
And that thickness is just a killer for performance. For you listening, 240 microns is about the thickness of 3 sheets of regular printer paper stacked up.
Right.
Liquid battery separators are way, way thinner. That extra thickness adds weight and resistance. It means that, in practice, current SSB designs just can't compete with the best liquid lives on overall performance.
Okay, so sulfides are fast, but they're toxic and too thick for now. What about the other two?
Next are the polymers. The good part is they're easier to manufacture and they make really good, stable contact with the electrodes. The big drawback is they have poor conductivity at room temperature. Which means commercial versions, like the Ball or Blue cars, they have to operate at high temperatures. We're talking 70 to 80 degrees Celsius, kept hot by an external heater.
Heating your battery to 80 degrees just to make it work. That seems to defeat the whole safety purpose, and it must drain extra energy.
It does. And finally, you have the oxides. These are great because they're stable against lithium metal and air, fantastic for safety and long life, but their drawbacks are crushing for cars.
Too heavy.
They're very high density, so they weigh too much, and they just cancel out the benefit of using lithium metal, and they're brittle, so it's hard to maintain good contact inside the battery as it expands and contracts. They have stability, but not the performance needed for a high-range EV.
So no silver bullet. It sounds like there's just a series of incredibly difficult trade-offs that these R&D teams are fighting with every single day. And while they're doing that, the current liquid leads are just continuously improving and fighting to keep up with this insane market demand.
And that huge demand is what's driving all this. The industry's vision for the 2030 EV is, well, it's aggressive. They're banking on one of these technologies having a breakthrough.
What are the actual goals? What are they shooting for by the end of the decade?
The sources are projecting that EVs will just dominate the market by 2030. Shares over 40, maybe 50% of all new cars sold. And the technical goals for new batteries are, they're phenomenal. An 800 to 1,000 kilometer range.
1,000 kilometers.
A 10-minute charging time.
And cost dipping below $75 per kilowatt hour.
To meet that kind of demand, the market is already incredibly competitive, and the landscape is shifting under our feet. Looking at 2025 delivery data, you can really see how Chinese manufacturers have just taken a dominant position.
This is the critical market context for you to see.
Yeah.
Based on 2025 global EV deliveries, BYD holds 19.9% of the market. Geely is second at 10.2%.
And Tesla?
Tesla is third at 7.7%. But what's significant is they saw an 11% decline in year-over-year deliveries in that period. The top 5 Chinese automakers already account for 43% of the entire global EV market.
And the sheer scale of this transition brings us right back to the sustainability problem. We're not just talking about car emissions anymore, but the production of this whole $400 billion industry. Exactly. The sources flagged 21 distinct ESG risks here. But the biggest choke point, as you mentioned earlier, is raw materials.
The lithium shortage.
Right. While there's theoretically enough lithium in the ground worldwide, meeting that 2030 demand requires what they call the full potential scenario of every single mining project. If that doesn't happen, the base scenario shows a severe 55% shortage of lithium by 2030.
That's an existential threat to the whole electrification timeline.
It is, and beyond just scarcity, there's the emissions paradox of making the battery itself.
What's that?
It's the second huge hurdle. While EVs have drastically lower life cycle emissions than gas cars, their production emissions, the mining, the manufacturing, are double that of a traditional car.
So we have to clean up how we make the clean car.
We have to. The industry needs to cut those emissions by up to 90% per kilowatt-hour by 2030. And that really comes down to 2 things: switching all the manufacturing to low-carbon electricity and maximizing the use of circular materials.
Which means the system just cannot be a take, make, dispose model for batteries. It has to be circular.
It must be. Repair, reuse, and recycle. It's not just about resilience against shortages, it's also a huge economic opportunity. Recycling alone is expected to create a $6 billion profit pool by 2040.
So what does this all mean for you listening? We hope we've given you a simple, clear story of the extreme competition that's happening right now. The race between the continuous, fast improvement of liquid lives and the disruptive high-risk potential of solid state. That's what's shaping the speed of the EV revolution.
And those 2030 targets, 10-minute charging, 1,000-kilometer range, They show the moonshot goals the industry has, even as it's staring down the barrel of a potential 55% raw material shortage and this immense pressure to cut manufacturing emissions by 90%.
It really raises this final provocative thought for you to consider then. The technical race seems to hinge on finding that extra 0.01% of efficiency in a lab. But the entire $400 billion market hinges on solving a 55% lithium shortfall on the ground. Which constraint do you think is going to break first, the microscopic science or the macro supply chain?
A really interesting question to think about.
Thank you for diving deep with us today.